Good morning and welcome to the Tactical Generator Monitoring System Sprint 4 review. Here's our agenda. And here is our team.
The Tactical Generator Monitoring System is a power monitoring device intended to save American lives. There are enemies inside the wire, and their names are wet stacking and overloading. Fuel must be brought to forward operating bases by ground vehicles in order to be cost efficient. This operation costs lives every year as insurgents plant improvised explosive devices and ambush caravans. Service men and women are fearing for their lives. This process can be reduced by using fuel and generators efficiently with our product. No country should allow deadly inefficiencies. Our vision is to create a product that can conserve fuel and prolong generator health in order to reduce the amount of dangerous caravans bringing fuel and generators to forward operating bases. Members of this project will lead these soldiers in a year. They are motivated to put out a quality, effective product as it may be their soldiers that are put in danger. This product has been developed by multiple classes of electrical engineering majors, IT majors, electrical engineering Army officers, and United States Military Academy professors. It was also presented at the Army Research Lab in the fall by Cadet Anderson. Our plan is simple. The Tactical Generator Monitoring System team hopes to create a monitoring system for all Army microgrids in war zones around the world. These systems will flawlessly integrate in their microgrids using a simple series connection between generators and loads. We promise to design the most robust, applicable product in our power. Please enjoy the progression of our project. The U.S. Army continues to be on the forefront of effective militaries. We will not waste the taxpayer money and lives.
The product background slide describes the why. The high-level product diagram describes the how. The TAC-Gen will measure the output of the military generator using straight plug and wall mount connectors. Current transformers will measure its current, and the voltage transformers will measure the voltage. The ADD converter outputs digital signals, and using C++ Fourier transform algorithms, we are able to calculate the phase and amplitude of the power. We can then do three things with this data: store them in a database, display them on a GUI, or analyze the data on a computer.
For our Sprint 4 goal, the goal of Sprint 4 is to produce testing results by integrating the assembled product with working code. The capacity, our expected hours is 147 hours calculated by the 6 cadets times 7 lessons times 3.5 hours. Our actual hours are 137.5 hours. For our scope, it is 0.935.
This is Cadet Peringer. In Sprint 4, I tested the current transformer, I tested the ADD converter, I finished the product logo with Tim Spear, I worked on the wiring for the current transformer, and I worked on the Sprint 4 video. There were a couple of changes in this sprint away from the plan. The ADD converter is going to need a DC offset, as it is not able to process negative values. I had to wire the current transformer with a large gauge in order to be able to handle our 50 amps rated value. And the current transformer testing was not finished and will need to be moved to Sprint 5 as the ADD converter testing took precedence. The final plan change was the ADD converter values will need to be put into a database to be analyzed. The sampling on the screen of the LCD is not fast enough to get an accurate look at what the ADD converter is measuring. So we will be working to add those values to a database and analyze them over a period of time in Sprint 5.
This is Cadet Stahl. In support of the Sprint 4 goal to produce testing results by integrating the assembled product with the working code, this sprint my focus was working with the other EEs on testing the AD converter, as well as testing the voltage transformer and managing the slides for this sprint presentation. We finished testing the voltage transformers and the A to D converter. I will continue to work with my teammates to integrate all our parts and build our design. I missed the last 2 lessons of the sprint competing in a Sanders competition in Mexico, so unfortunately was unable to complete all my hours for this sprint.
This is Cadet Anderson. For this sprint review, I had a number of goals to complete. I needed to revise the voltage transformer test plan and test the voltage transformer in order to meet our voltage specifications for the Raspberry Pi. I had the end goal of wanting to create a printed circuit board for electrical design. However, I ran into a number of issues in my voltage transformer testing that prevented me from being able to complete my list of goals and required I make additions to the things I needed to complete during this sprint. When I ended testing my voltage transformer, we came to the realization that the Raspberry Pi would not be able to accept a sinusoidal waveform that included negative values. For this reason, we realized that we would have to make a DC voltage offset circuit that would shift our sinusoid upward within the range of 0 to 3.3 voltage limitation. For this reason, I have not completed testing of the voltage transformer component, nor was I able to generate the requisite PCB for this sprint. This slide demonstrates the voltage divider that is being implemented in this current circuit. Since the 6.3 volt voltage step-down capability of the transformer was not stepped down enough for our needs, we needed to create a voltage divider in order to step it down even more. In my testing, I realized that the actual voltage on the secondary windings when paralleled was approximately 8.47 volts. From there, I was able to choose resistor component values that would set my voltage to the required value. Dr. St. Ledger was able to provide a site that helped me understand the problem we would face with needing to provide a DC offset to the sinusoid and shift the sinusoid up so the negative values of the sinusoid were not included in the Raspberry Pi's input. This is currently a work in progress and will require me to change my voltage divider to half of what it currently is. The circuit should be completed before Sprint 5 begins. Though I wanted to complete a printed circuit board for the sprint, I was not able to do so. However, Cadet Jared Fritz gave me a valuable refresher tutorial on how to create a PCB and ULTI board. I feel confident in being able to complete this design once I have completed and tested both the voltage divider and voltage offset circuits.
Hi, this is Cadet Sun. So for the research C++ code, that was not integrated into Segment 10 Stark's Arduino code. We ran into issues where Arduino could not compile some of the C++ language that was written. Changing the pin numbers for the AD converter compiled, but there's functions that the Arduino will not compile into binary. We're working to see if there's an override to compile the written code so a binary output is generated for the Raspberry Pi to read. For my C++ digital signal processing research, I needed to figure out how to take sample digital signals from the AD converter and create an algorithm to sample the digital signal at 60 Hz. This is called windowing. So the book I used gave me several windowing routines, such as the Hamming window code that's displayed above. This code essentially tapers endpoints to create a window of a signal to be analyzed. Once this window is created, we can perform a discrete Fourier transform. So the following code next to DFT code shows what it does is it combines the calculation of power magnitude, log magnitude, and phase. The magnitude is then placed in the real part of the input array, and the phase is in the imaginary part, and the log magnitude is in a separate array from that.
This is Cadet Bondoc. For this sprint, I worked with Cadet Munkter and Cadet Sun with the implementation and testing of the AD converter and the functioning code for the Raspberry Pi. Following the advice of our product owner, we prioritized the testing of the AD converter. We did this because the AD converter is the key component between the generator and our Raspberry Pi. We ran into several issues when testing our AD converter. For example, it took us several hours to realize that we had fried our AD converter. Luckily, we had several spares, and we were able to, once we replaced our AD converter, we were able to run our initial code. I also spent time configuring the base Raspberry Pi code. For the next sprint, we need to create a database that will store the values from the AD converter.
This is Cadet Mukhtar. During Sprint 4, I was tasked to test the analog to digital converter code and run Arduino size recommendation code on Raspberry Pi. I was able to complete my task, but I was not able to combine both codes and get results. This is the first test code that I ran. We can use this code to create our dataset. This is the second test code for our analog to digital converter. And this is last year's size recommendation code running on Raspberry Pi instead of Arduino.
Our goal for Sprint 5 is we hope to finish testing the current and voltage transformers, assemble a usable prototype. We want to add extra emphasis to getting the code done. Once we have these AD converter values confirmed, we're going to need to test them in our Fourier transform algorithms in order to sample and correctly get a phase and amplitude for these signals. We're going to need to begin final assembly and leave time for unexpected debugging. The real emphasis is that we are going to need to have a finished prototype coming up towards Projects Day and for the Soldier Design Competition semifinals.
This is our product roadmap. As you can see, we are slowly reaching the end of our product roadmap.